Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, so today we will continue with the fourth chapter, which is the diode chapter. So today we will cover on the second part of chapter 4, which is the diode applications. Okay, so in the second part of the chapter 4, we will actually cover on the diode applications. Okay, so these diode applications will cover the load line analysis, series and parallel diode configuration, half-wave rectifier, full-wave rectifier, clippers, and also clampers. Okay, so basically for today, for this video lecture, I will cover on the load line analysis, series and parallel diode configurations, half-wave rectifier, and also a part of full-wave rectifier. Okay, so this one I name it as part 2A, and clippers and clampers, we will have another video, like video lecture, which I name it as part 2B. Okay, so for this lecture, we will cover up until the full wave rectifier. Okay, so without wasting time, let's just directly go into the what is load line analysis. So stated over here, if the analysis is performed in a graphical manner, a line can be drawn on the characteristics of the device that can represent the applied load. Okay, so I hope that you guys still remember what is VI characteristics of a diode. Okay, so if you still remember in chapter 4 part 1, okay, you have learned on the VI, the voltage current characteristics of the diode. Okay, and you should know the graph of the VI characteristics. Okay, and over here it stated that the intersection of the load line with the characteristics will determine. Okay, so the main point over here, the intersection of the load line with the characteristics will determine the point of operation of the system, where we usually call it as a quiescent point or Q point. Okay, so usually we call it as the Q point. This is the intersection of the load line with the characteristics. This characteristics is the VI characteristics that you have learned previously in chapter 4 part 1. Okay, so all of this analysis is what we call as the load line analysis. So the load line is used to determine the current and also the voltage in a diode circuit. Okay, and from the Q point, we can actually determine the diode voltage VDQ and also level of current IDQ. Okay, so if you look at here, this is the load line. The black line over here is what we call as the load line. Okay, and this blue line over here is the characteristics, the VI characteristics. Okay, so if you still remember the VI characteristic of a diode in chapter 1, chapter 4 part 1, you will have something like this. Okay, something like this. Okay, so if you don't remember, I hope that you can refer back to the previous slide, okay, on the VI characteristics. Okay, VI characteristics, or we also call it as the VI curve, okay, where it actually shows when the diode is in forward bias or reverse bias. Okay, So you have two lines over here. The first one is the load line. This one is the characteristics. Okay, so from the previous slide, okay, it stated that the intersection between the load line and the characteristic we call as the Q point. Okay, we call as the Q point. And from the Q point, we can determine the diode voltage, which is the VDQ. Okay, so from this Q point, you can determine the diode voltage, VDQ, and also the diode current, IDQ. Okay. So how can we actually determine the load line intersection? Okay, how can we actually determine the load line intersection? For example, given a circuit, this is a simple diode circuit, yeah. So this you have a voltage source, this is the diode, and this is a load resistor. Okay. So from this circuit, by using Kirchhoff voltage law, okay, Kirchhoff voltage law, you will get the KVL equation, okay, where E is equals to VD plus VR. Okay. Okay. So you do the KVL equation for the circuit, you will have negative E plus VD plus VR is equals to 0. So VD plus VR is equals to 0. Okay, and VD plus VR is actually ID. R is equals to 0. Okay, ID is the current across the diode over here. So since this is a series circuit, so the current is the same. Okay, so by using KVL, you will get E equals to VD plus ID R. Okay, and the intersection can easily be determined by employing anywhere on the horizontal axis, ID is equals to 0. And anywhere on the vertical axis, VD is equals to 0. Okay, so first, for example, we set VD is equals to 0. Okay, so when we set this VD is equals to 0, this equation, okay, so VD is equals to 0, so this will become E equals to 0 plus IDR. Okay, and you will get ID is equals to E over R. Okay. Next, you set the ID is equals to 0. So when ID is set equals to 0, okay, the KVL equation will become E equals to VD plus ID is 0 multiplied with R, you will get 0. So VD is equals to E. Okay, so that's why from this graph, the load line analysis graph, you can see that when ID is equals to 0, this is ID. So when ID is equals to 0 over here, VD is equals to E. This one, when VD is equals to 0, that's why you will get ID is equals to E over R. Okay, so this is the derivation. How do we get this? The intersection, zero intersection. Okay, so when ID is equals to 0, VD is equals to E. When VD is equals to 0, ID is equals to E over R. So the intersection of the load line with the characteristic will determine the point of operation. Okay, so after you know that when ID is equals to 0, when VD is equals to 0, ID is E over R, and when ID is equals to 0, VD is equals to E. So you know these two value, and you can draw this line, then only you can draw this line. Okay, so the intersection of this characteristic line with the load line, you will get the Q point, and you can determine the VDQ and also the IDQ, which is the point of operation of the diode, the system. Okay, so this is actually depends on the circuit. Okay, so this value is valid for this kind of circuit, this simple circuit. Okay, so now let's look at the example. So given this circuit, so this circuit is similar to the previous circuit. Okay, you have the voltage source, diode, and also load resistor. So the question is for the series diode configuration in figure 7 and the characteristics in figure 8. Okay, so this is the diode circuit in figure 7, and this is the VI characteristics of the diode in figure 8. Determine the VDQ, IDQ, and also VR. Okay, so remember your load line analysis graph. So over here, you already know the characteristic curve. Okay, so you can draw the characteristic curve over here. Okay, but now you need to determine the load line. Okay, so in order to determine the load line, you need to determine this intersection. Okay, the value of the VD when ID is equals to 0, and also the value of ID when VD is equals to 0. Okay, so first let's calculate for the ID over here. Okay, so the derivation is actually already shown in the previous slide. Okay, so over here we just use the formula ID E over R because we already know that when VD is equals to 0, the ID here is E over R. Okay, so E is 10 volt, R is 0.5 kilo ohm. So 10 divided by 0.5 kilo ohm, you will get 20 milliamp. And for the VD over here, when ID is equals to 0, you know that VD is equals to E. So VD is equals to 10 volt. Okay, so then only you can draw the load line. So the intersection between the characteristics curve and the load line, you can get the Q point. And from the Q point, you can actually obtain the IDQ and also VDQ. Okay, so based on this plot, VDQ is approximately 0.7 volt, 0.78 volt, and IDQ is approximately 18.5 milliampere. Okay. So that one is VDQ and also IDQ. And the question asks you to calculate for the VR. Okay, so for the VR over here, the KVL equation of this circuit, you have negative E plus VDQ plus VR equals to 0. Okay, so VR is actually E minus VDQ. Okay, so over here, why we use VDQ instead of VD? Why do we use VDQ instead of VD? because VDQ is the operating point. Okay, VD is the value of the voltage when ID is equals to 0. But the operating point is the VDQ and also the IDQ. Okay, operating point is the Q point. Okay, so at the Q point, VDQ is 0.78, IDQ is 18.5 milliampere. So you must take note that in order for you to calculate for the VR over here, you need to make sure that this is VDQ. Okay, VDQ is actually the diode voltage at the Q point. Okay, so 10 minus 0.78, so you will get 9.22 volt. Okay, so I hope that you can understand example 2. Okay, so another parameter that you can also determine is the DC resistance. Okay, so over here, the DC resistance can also be found from the Q point value. Okay, so DC resistance is actually the RD, the resistance, okay, at the Q point. So in order to calculate for the resistance, you must divide VDQ divided by IDQ, because you know that V equals to IR. So R is equals to V over I. Okay, so this is VDQ and IDQ. VDQ is 0.78, IDQ is 18.5, and you will get the resistance, DC resistance is 42.16 ohm. Okay, so from this circuit you can actually redraw to its equivalent circuit, which is equals to this. Okay, so you have the voltage source, is load resistor, and this is actually the diode. Okay, however, we convert into the DC resistance with the value 42.16. Okay. Next, let's look at the series diode configuration. Okay, so in this part, the approximate semiconductor diode model is used for the analysis. Okay, so basically we have two models. Okay, for diode calculation. The first one is approximate model. The second one we call as the ideal model. Okay. So if you still remember the diode VI characteristics, so for the approximate model, okay, this we have what we call as the knee voltage over here. Okay, the forward bias over here starts at 0.7 volt. This one, the voltage here actually depends on the materials of the semiconductor used. Okay, so 0.7 is the voltage for the silicon. Okay, Si is the silicon. But for ideal model, the forward bias over here starts exactly at 0. Okay, so that is the difference between approximate model and also the ideal model. Okay. So remember, for diode we have forward bias, we have reverse bias. So this part here is what we call as the forward bias. Okay. So for example, this is your diode. This is a silicon diode because this is the approximate model. So for silicon, the voltage is 0.7 volt. Okay. So during forward bias, we have the circuit will become something like this. Okay, so we have voltage 0.7 volt over here. But at this part, this is the reverse bias. Okay, so during reverse bias, this circuit over here will act as an open circuit. Okay, where the current over here is 0 ampere because it's open circuit. Okay. For this one, this is the ideal model. So based on the ideal model, during forward bias, okay, so since the voltage is 0, okay, so during forward bias, we assume this as a short circuit, okay, short circuit. So when short circuit, the voltage is equals to 0. But during the reverse bias, the circuit will, the diode will become as an open circuit where I is equals to 0. So now let's look at the what happens in a diode circuit during forward bias. Okay, so over here you have this diode circuit. This is a very standard basic diode circuit. Voltage source, diode, load resistor. So over here it stated that by substituting the equivalent model for the on-state diode, the VD is equals to the knee voltage. Okay, so first let's do for the forward bias. So if you remember, okay, so because over here it already stated the silicon, so we should use the approximate model. Okay, because of given here the material of the diode, which is silicon. Okay, so remember, based on the previous slide, during forward bias, this diode will act as the voltage source. Over here you have, this is 0.7 volt, okay, depending on the material. Okay, so when you do KVL over here, you will get VR is equals to E minus V. This is actually VD, okay? But since during forward bias, the VD here is equals to the VK. VK is the knee voltage, VK. VK is depending on the material of the diode. For this one, we use silicon, so the voltage is 0.7 volt. Okay, so VD is equals to VK, so that's why you will get VR equals to E minus VK. Okay. And the ID, diode current over here, this is a series circuit, so I current through the diode is the same as the current through the resistor. Okay, so you can calculate the current, the voltage VR divided by R, and you will get the current, diode current ID. Next, what happens during reverse bias? Okay, what happens during reverse bias? So, during reverse bias, okay, so when reverse bias, the symbol of the diode should be like this, the opposite of the forward bias. Okay, so during reverse bias, what happens is that this diode will become an open circuit because ID is equals to 0. Okay, this will become open circuit, so ID is equals to 0. Okay, so when you do KVL over here, no, you cannot, because this is already open circuit. Okay, so you VR, you can determine the VR. VR is IR multiplied with R. Since this is series circuit, so IR is the same as ID. Okay, and you know that ID is equals to 0. Okay, so when ID is equals to 0, VR is equals to 0. Okay, so the VD is equals to E because negative E plus VD plus VR equals to 0. So VD plus VR is equals to E. Okay, and VR over here is 0. So this becomes 0. So VD is equals to E. Now let's look at example 3. So for the series diode configuration in figure 9, determine VD, VR, and also ID. Okay. So given this circuit, so the VD over here, because this is forward bias, okay, so the VD is equals to the knee voltage, okay. VD is equals to VK. So VK is, since this is silicon, so VD is equals to 0.7 volt. Okay, for VR, you need to do KVL. So VR is equals to E minus VD. Okay, VR is E minus VD. So E is 8 volt, VD is 0.7. You will get VR equals to 7.3 volt. Okay, and lastly, you can calculate for the ID. So ID is the current here. So it is the same as the current that flows here, current IR. So IR is equals to VR divided by R. So VR you already calculate 7.3. So R is 2.2 kilo ohm. You divide, you will get ID is equals to 3.32 milliampere. Okay. Okay, so next let's look at the source notation. Um, okay, for this one, this is just to show you a different way how we can actually represent a voltage source. Okay, so usually for a voltage source, we use this symbol. Okay, use this symbol for a voltage source. But sometimes in a circuit, instead of uh, drawing the voltage source symbol like this, we use a circle like this. Okay, for example, okay, and I label this as positive 10 volt. Okay, so instead of I draw the voltage source like this, I just draw it a single line like this. Okay, still it is still the electrical circuit. Okay, so when you have a symbol like this, when you have E equals to 10 volt, so the symbol is actually like this. Okay, plus minus 10 volt. But if it's negative, okay, so the symbol is like this. This is negative and this is positive. Okay, so this is the difference between positive and negative. So in example 4 over here, so you look at here, given a circuit like this, okay, so instead of using the normal voltage source, we use this kind of notation for voltage source plus 0.5 volt. But if you redraw this, you actually have a circuit like this. Okay, you have a circuit like this. It's actually a voltage source, and then you have a diode circuit, you have a ground. Okay, so this is actually the same. Okay, this is the same thing. This is the same circuit. Okay. So example 4, for the series diode configuration in figure 10, determine VD, VR, and also ID. Okay, so determine VD, VR, and also ID. So if you look at here, this is actually a reverse bias. So during reverse bias, the diode over here will become open circuit. Okay, so since this is open circuit, then the current is equals to 0. Okay, the current is equals to 0. Okay, and you can calculate for the VR. So VR is IR multiplied with R. IR is equals to ID. However, ID is equals to 0. So VR is equals to 0. And then you can calculate for the VD, okay, using the KVL. So since the VR is equals to 0, so VD is actually equals to E, which is equals to 0.5 volt. Okay. Okay, so this one actually, if the diode is like this is uh, forward bias actually. Okay, you must change this as this, like this. I know. Correct? Yeah, correct. Okay, you must change it like this. Okay, so the example, there's a correction for the example. This answer, okay, the diode must be like this. Okay, because the answer is for reverse bias. Now let's do example 5. Okay. So for example 5 over here, this is forward bias. Okay. Previous slide, this one you must change it to reverse bias. Okay. This is forward bias. Given this circuit, determine V naught and ID for the series circuit in figure 11. Okay, so the V naught is over here. So um, it is actually V across the 680 ohm resistor. Okay, so if you redraw this, you actually have something like this. Okay, and V naught is actually the V over here. Okay, so you need to determine the V naught. So V naught is actually the V across the 680 ohm. Okay, so by using KVL, okay, you will get negative E plus VK1. This is VK1. This is VK2. Okay, both of this is a diode. Okay, VD. Okay, but however for this one during forward bias, the VD is equals to VK. Okay, so since VK is knee voltage. Okay, so knee voltage depends on the material. Okay, so over here, the first VK, before that, let me write the KVL equation. This is VK2 plus V naught. Okay, so V naught is over here. V across the resistor. Why? Because this is parallel. So the voltage here is the same as voltage across the resistor equals to 0. So you will get V naught equals to E minus VK1 minus VK2. Okay, so for VK1, this is silicon. Okay, silicon. So E is 12. So 12 minus silicon is 0.7. Okay, however, this is a LED. LED is also a diode. So the LED here, the color is red. So you refer to this table for the red, the material is GaAsP and the voltage is 1.8. That's why you will need to the minus 1.8 and you will get 9.5 volt. Okay. This is V naught. Okay, and you can calculate for the ID. So ID is equals to IR. I across D is the current across IR. So IR is VR over R. VR is the same as V naught. So you will get ID is equals to 13.97 milliampere. Okay. Next, let's look at example 6. Okay, so for example 6 over here, given this circuit, determine ID, VD2, and also V naught for the series circuit in figure 12. So if you look at here, this is forward bias, however, this is reverse bias. Okay. So if forward bias, you can just maintain it like this because you have the voltage VD is equals to VK over here. However, for the diode with the reverse bias, the circuit here is an open circuit. Okay, because it's reverse bias. Okay, so the first question, I want to calculate for the ID. So ID is the current that flows through this series circuit. So since you have an open circuit over here, you will directly know that no current flow in an open circuit. So ID is equals to 0 ampere. ID is equals to 0 ampere. For the V naught is over here. So V naught is the same as V across R. Okay, so it is IR multiplied with R. IR is the same as ID. ID is 0. Okay, 0 multiplied with R, you will get V naught is equals to 0. Okay, and your question asks you to calculate VD2. So VD2 is equals to E minus VD1 minus V naught is equals to 0. So this one is actually, you need to change it to 0.7 actually, because over here it stated that the material is silicon. But if the material is not given, then you can use 0. Okay. Next is exercise 7.4. Determine I, V1, V2, and also V0 for the series DC configuration in figure 13. Okay, so the first one, calculate for the I, the current. Okay, so to calculate for the current, you can do KVL. Okay, you do KVL, you will get the answer 2.0.7 milliamp. Okay, I want you to do the KVL by yourself. You should get the current 2.07 milliamp because you're already familiar with KVL before this. Okay, so after you obtain the current, you just use the KVL. Okay, you will get this. So you can calculate for V1. V1 is over here and also V2. Okay, so V1 is I multiplied with R1. So you will get 9.73 volt. For V2, I multiply with R2. So you get 4.55 volt. Okay, next you want to calculate for the V0 over here. Same, you do a KVL over here. So you will get this KVL equation, negative E2 plus V2 minus V0. And you will get V0 equals to V2 minus E2. So your final answer should be negative 0.45 volt. Okay. Next is example 7. Given the circuit figure in figure 14, determine V0, I1, ID1, and also ID2 for the parallel diode. Okay, so the previous example, this is series diode. This one is parallel diode configuration. Okay, so you can see that the diode here, we have two diodes, D1 and also D2 is connected in parallel. Okay, actually the calculation is the same. Okay, just the difference is the parallel series connection. Okay, so determine V0, I1, ID1, and also ID2. So the first one over here, you can calculate for the V0. So the V0 is the V over here. So since this is parallel, so the V0 is actually the same as the VD here, VD that flows through the D2 and D1 over here. Okay, so the VD, remember, this is forward bias. So VD is equals to VK. So VK for a silicon is 0.7. So V0 is equals to 0.7 volt. Okay, next you can calculate for I1. I1 is over here. So I1 is the current, you can say that is the current that across the R over here. So VR divided by R. VR is E minus VD. Okay, KVL. E minus VD divided by R. So you will get 28.18 milliampere. Okay, and this one, ID1 and also ID2. So in order to determine ID1 and ID2 is basically I1 is equals to ID1 plus ID2. Okay, so since ID1 and ID2, the value should be the same, okay, because the material is the same, silicon, the voltage VD is the same, which is 0.7, then ID is I1 divided by 2. Okay, for example, this is ID1 plus ID2 because ID1 and ID2 is the same, so I label this as ID1. Okay, so this will become 2 ID1. Okay, so ID1 is actually I1 divided by 2. So that's why you have I1 divided by 2, ID1. Same for ID2. Okay, so you will get 14.09 milliampere. Next is example 8. Okay, so given this circuit, determine the current I1, I2, and also ID2. Okay, I1, determine the current I1, I2, and also ID2. So I1 is over here. Okay. So I1 is actually VK2 divided by R1. Okay. Why? How do we get VK2 divided by R1? It's actually using KVL. Okay. Using KVL, you will get this I1 is equals to VK2 divided by R1. So equals to 0.212 milliampere. Okay. For VR2 over here, also you do a KVL over here. Okay, so you will get VR2 is equals to E minus VD1 minus VD2. This is silicon, so 0.7 minus 0.7, so you will get 18.6 volt. For I2 is over here. This is actually VR2 divided by R2. So you will get 3.32 milliampere. And lastly, ID2 is over here. So ID2 is I2 minus I1. So over here, this is I2, this is I1. Okay, so ID2 is I2 minus I1. So you will get 3.11 milliampere. Okay, so this is actually questions from the tutorial. Okay, so I'm not sure whether I already uploaded the tutorial, but if not, I will upload it. I will upload the tutorial for after this. Okay, so this question is actually from the tutorial number 15B and C. Okay, so what I want you to do, I want you to do it by yourself and you should get this answer. Okay, actually the already given here. Okay, you should find I. So the answer for I is 2.895. For question 15C, I equals to 1 ampere. So please do your tutorial. Okay, you must determine which one is forward bias, which one is reverse bias. Same as this one. This is also the questions from the tutorial. This is question 16A and 16B. Given this circuit, find the V naught. Okay, so actually you already been given the answer. So I want you to do it by yourself. Okay, and also tutorial number 17, 18, 19, and also 20. Okay, so please do it by yourself. Later at the end of this chapter, then only I will share with you the answer for the tutorial. Okay, but please make sure that you do it by yourself first after this lecture. Make sure that you understand how to calculate. So the calculation for the diode circuit is very, very important for your final exam. So please make sure that this lecture today, the calculation for the diode is very important for you to know and understand. Okay. Next, let's go to the rectifier. So rectifier is actually the applications of the diode. Okay, the diode, one of the application of a diode is it is used to build a rectifier. Okay, so what is rectifier? So rectifier is a device that convert alternating current to direct current. So you know that AC is like this. AC is a straight line. So the function of rectifier is to convert AC to DC. Okay, so the process of converting AC to DC is what we call as the rectification. Okay, so rectifiers are used as the component of the DC supply and high voltage direct current power transmission. Okay, so why do we need rectifier? Because most of the applications that we use in our daily life requires a DC current. However, the supplies that we get from our uh, voltage source is a AC. So that's why we need a rectifier in order to convert from AC to DC. So the output of the rectifier is smoothed by an electronic filter to produce steady DC current. And basically there are two types of rectifier. The first one is the half wave rectifier. The second one is full wave rectifier. So later we will look at the difference. What is half wave rectifier? What is half wave rectifier? So now let's look at half wave rectifier first. So half wave rectifier circuit consists of one diode. Okay, so this is the half wave rectifier circuit. Okay, it uses only a single diode. Okay, so it produces one sine pulse for each cycle of input sine wave. So this is your input, yeah. Remember, the input is AC. You want to convert it to DC. This is the input, AC signal, V in. Okay, now you and the output here is the V naught. Okay, so this is a one cycle of alternating current. Okay, and the from this point to this point, the time is T. Okay, the time is T. So this point over here is actually T over 2. Okay, so now let's see how a half wave rectifier works. So first we divide it into two regions. Okay, the first part we call as the conduction region. Okay, from time 0 to time T over 2. Okay, the first part here. Okay, we call as the conduction region or the forward bias. Okay, so when the input sine wave goes positive, okay, here, the input sine wave from 0 to T over 2, the input is positive. So we call this as a forward bias. Okay, so in forward bias, the diode conducts like a closed switch. So the diode over here will conduct as a closed switch like this. Okay, so the diode letting the positive pulse of the sine wave to appear across the load resistor. So from this circuit, you get this circuit and you can actually get the V naught. Okay, so V naught here is actually equals to V in. Okay, V naught here is equals to V in. Okay, so this is the output. So this output will follow V in at time 0 until t over 2. Next, from time 2 to t, time t over 2 until t, we call as the non-conduction region or the reverse bias mode. Okay, so the second part over here, the voltage, the V in here is negative. Okay, so it is reverse bias. Okay, so in reverse bias, the diode will become open circuit, therefore no current flow in the circuit. Okay, so from this circuit, for reverse bias, the diode over here will become open circuit, so no current flow. Okay, so when there is no current flow, automatically you can see that the V naught here is equals to 0. So that's why the output over here at times t over 2 until t, the V naught is 0. Okay, so if you want to, so over here, okay, so the figure over here actually shows you what happens in the half-wave rectifier. This is the input. This is the V in, this is the V out. This is the input, this is the output. So the input is AC, sine wave. Okay, but the output over here will become something like this. Okay, because this is forward bias. During reverse bias, V naught is equals to 0. Okay, and this is the second cycle, and so on. Okay, so the VDC of this half-wave rectifier, the value here, this is fixed. The value is V 0.318 Vm. Vm is the V maximum over here. Okay, Vm is the peak voltage. Okay, so the VDC of the half-wave rectifier is fixed at 0.318 Vm. So in the previous circuit, okay, it is a half-wave rectifier without the effect of silicon diode, because this diode over here, we don't know whether the material, we don't know whether it's a silicon or what material. So we assume it as no effect of silicon diode. Okay, we assume it as 0 volt. Okay, but what happens if we have the effect of using a silicon diode? Okay, so when the applied signal must be at least 0.7 volt before the diode can turn on. Okay, if the input is less than 0.7 volt, the diode still open circuit and the output voltage is 0. During conduction, the difference between input and output voltage is Vk, the knee voltage 0.7 volt. Okay, so what it means here, the diode here, you have the knee voltage 0.7 volt. Okay, so in the previous slide, for the half-wave rectifier without the effect of silicon diode, this is the input, and the output you will have something like this. Okay. However, if you have a silicon diode, meaning you have 0.7 silicon diode, what happens is that at the output, okay, there will be a offset. okay, due to the knee voltage, okay, because the knee voltage is 0.7. If there's no effect of silicon diode, this will end at 0. However, because of the silicon diode, the Vk is 0.7. Okay, so when the difference is at the output, there will be a small gap, or we call as offset. Okay, yes, yes, and then you add another one. So you have an offset. If there's no silicon effect of silicon diode, then there will be no offset. And the VDC will become 0.318 V naught minus Vk. V naught M minus Vk. But for without the effect of silicon diode, VDC is 0.318 Vm. Okay, V naught M is actually Vm. V naught M. Okay. This one 0.318 Vm minus Vk. You need to minus the knee voltage. This one no need to minus the knee voltage because the Vd is 0. Okay, so that is the difference when you have the effect of silicon diode. Okay, so this is the difference between ideal diode model and also for this one we call as the approximate. Okay, this is approximate because you take into consideration the silicon equals to 0.7 volt. This one is ideal diode model. So this blue line is the output. Okay, this is the input and the blue line is the output. This is for ideal diode model. But for if you take into consideration the silicon diode effect, then if you look at here, there will be a voltage drop and also there will be an offset. Okay, there will be an offset and also a voltage drop. So now let's look at example 9. Refer to figure 16, sketch the output voltage and determine the DC level of the output of the circuit. Okay, so from this figure 16, you know that this circuit is a half-wave rectifier circuit. Okay, so how to sketch the output and determine the DC level? So you know that this connection over here, the diode connection, this is reverse bias. Okay, this is the reverse bias. So what happens is that during positive cycle, Vd, Vout is equals to 0. Okay, but during negative cycle, Vout is equals to Vin. Okay, this is positive cycle, Vout equals to 0. Negative cycle, Vout equals to Vin. Okay, because there is reverse bias. Okay, different from this one, the previous one here. This is forward bias. Okay, so that's why you during positive cycle, V out equals to V in. During negative cycle, V out equals to 0. But this one, this is reverse bias. So during positive cycle, V out is equals to 0. Negative cycle, V out equals to V in. Okay. So this is the output voltage. We just sketch it like this. Okay, and the question asks you to calculate for the DC level of the output. Okay, so because it doesn't state whether to consider it as an ideal diode or silicon diode, so the answer here, it gives both for the ideal diode and also silicon diode. So if you consider the diode as an ideal diode, so your VDC will be is equals to negative 0.318 volt. Okay, why there is negative? Because it's a reverse bias. If it's forward bias, no negative. Okay, so 0.318 multiply with Vm. So the Vm here is 20 volt. Okay, so the maximum. Okay, so equals to negative 9.36. But if you consider the diode as a silicon diode, then you need to use this formula, negative 0.318 Vm minus Vk. So Vk for silicon is 0.7. So you will get negative 6.14 volt. Okay, so you have a negative here because it's a reverse bias. Okay, so next, up to this point, you can do tutorial number 23 and tutorial number 24. Okay, and the previous one is a half-wave rectifier. This one, let's continue with the full-wave rectifier. So full-wave rectifier has two types. We have bridge rectifier and also center tap transformer. Okay, so in this video lecture, we will cover up until the bridge rectifier. Center tap transformer, we will cover in the next video lecture. Okay, so this is the circuit for a bridge rectifier, bridge full wave rectifier. So in half wave rectifier, you just use one diode, but in a full wave rectifier, you need to use 4 diodes. Okay, 1, 2, 3, and 4. So what happens in the full wave rectifier? So look at here, during positive cycle is this part. Okay, during positive cycle, diode D2 and D3 are forward bias. Okay, so it is can be converted into a closed switch. And diode D1 and D4 is a forward reverse bias. Okay, so reverse bias, it acts as a open switch. Okay, so that's why if you withdraw this, you will get a circuit like this. Okay, this is closed, this is open. So the current flow will flow like this. Okay. And you can calculate for the V0. So if you calculate for the V0 is here. So V0 is equals to Vm during the positive half cycle. During the negative half cycle, okay, this is the negative half cycle. During negative half cycle, D1 and D4, this is D1, this is D4, are forward bias, so it acts as a closed switch. And D2 and D3 is a reverse bias, so it acts as a reverse open switch. Okay, so for forward bias, for negative half cycle, this one is already inverse. Okay, so this is negative, this is positive, so the current flow from positive to negative. Okay, So you can calculate for the V naught. So V naught is also equals to Vm. So the output of the full wave rectifier should be like this. For a half wave rectifier, is like this. Okay, so that is the difference between full wave rectifier and also half wave rectifier. So this is the full wave rectifier without silicon effect. So when you have a full wave rectifier without a silicon effect, you can calculate for the DC level, VDC. This is fixed. Remember, VDC is equals to 0.636 Vm. Okay, but since this is a full wave rectifier, you need to this is 0.636 Vm. Okay, it is actually multiply by 2. Remember, the half wave rectifier is 0.318 Vm. So for the full wave, you need to multiply with 2. So you will get the VDC for a full wave is 0.636 Vm. So, and if you consider the effect of using silicon diode, so if the diode is silicon, then over here, instead of it becomes a closed switch, now the voltage here is 0.7. So you need to consider the voltage decay over here. So the VDC, if you take into consideration the effect of using silicon diode, the equation for the VDC for full wave rectifier is 0.636 multiplied with Vm minus 2 Vk. Okay. So you need to multiply with 2 for the Vk here because you have 2 diode. For half wave rectifier, you only have 1. Okay, so let's look at example 10. Determine the output waveform for the bridge circuit in figure 17 and calculate the output DC level. Okay. So you look at here, this is the full wave rectifier. You have 2 diode and you have 3 resistor. Okay, so instead of having a diode over here, we have a resistor here. Okay, so in order to solve for this, you need to solve it cycle by cycle. So during the positive cycle, okay, the positive cycle here, the diode here is a forward bias and this one is reverse bias. So this will become open, this will become closed circuit. Okay, so if you redraw this circuit, you will get this circuit. Okay, so you can calculate for V naught. Okay, I will not calculate for the V naught, you calculate for the V naught yourself. Okay, but actually over here, you already know that V naught is equals to 5 volt. Okay, so during positive cycle, you have a 5 volt. And then during negative cycle, it will be inverse. Okay, this will be short circuit, this will be open circuit. Okay, and you will have another 5 volt. Okay, and you can directly calculate for the VDC, where the VDC is 0.636 multiplied with Vm and your VM is 5. So you will get 3.18 volt. This is, I think this is the tutorial question number 27. Okay, this one I think I want you to do it by yourself and try to understand by yourself, because this is also questions in your tutorial. So if you look at here, the question asks you to sketch the V0 waveform for the circuit in figure 7.7 and determine the DC voltage. Actually, the how to solve for this one is similar to this one. Okay, you need to do it step by step. First the positive cycle and then the negative cycle. And then you can calculate for the V0 and also the VDC. Same for this one. And same for this one. Okay, so actually you already have the answer, the calculation in this slide. Okay, you just do it by yourself and compare it with your result. Okay, the step is all the same. The step is the same as this one. Okay, so basically that's the end of our chapter 4 part 2a. Okay, and this one I will cover it in chapter 4 part 2b. Okay, so chapter 4 part 2b will cover, we start with the full wave rectifier, center tap transformer. Okay, so if you have any question, you can ask me in the Telegram group or can ask me personally. Okay, so thank you very much, and we will continue in chapter 4 part 2b. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.